To understand the physics behind the electromagnetic train, it is important to understand magnets and magnetic fields. A magnet is made out of two poles, a north pole and a south pole. All magnets must have these two poles, and it is impossible for a magnet to have only one pole. When splitting a magnet in half, you do not end up with a north pole and a south pole. You actually end up with two separate magnets, each with its own north and south pole. Keep splitting and you will eventually end up with a single electron. Turns out, this electron has its own north and south pole. This essentially means that an electron is a magnet. The importance of these poles is that opposite poles attract. A north pole will attract the south pole, and a south pole will attract a north pole. If you have played with magnets before, you will know that sometimes magnets seem to push each other away. This is because the same poles repel each other. A north pole and a north pole will repel each other, and a south pole and a south pole will repel each other. Now that you understand the basics of magnets, let's move on to magnetic fields. A magnetic field is the area around a magnet that will exert a magnetic force on objects that come in contact with it. Knowing this, it is very important to understand how to interpret a diagram of the magnetic field. The object in the center is a magnet with north and south poles labeled respectively. The lines around it are the magnetic field represented in vectors. These vectors represent the forces that would be exerted on a north pole anywhere in the magnetic field. Before moving forward, it is extremely important to understand that these diagrams of magnetic fields are purely theoretical, as it is impossible to have only a north pole, as electrons have both a north and south pole. Since the diagram is based on a singular north pole, it is theoretical. Notice that in the diagram, as the vectors get further away from the magnet, the distance between each vector tends to increase. This is because, as you get further from a magnet, the magnetic force of it decreases in strength. This means the closer the vectors are to each other, the stronger the force. As stated before, the vectors represent the force on a north pole anywhere in the magnetic field. So how does one create this diagram? Putting a north pole particle in the magnetic field, the blue line represents the repulsion it feels from the north pole of the magnet, and the red line represents the attraction it feels from the south pole of the magnet. Using vector addition, we can determine that the net force on the north pole is the purple line. Do this same process in every possible location, and you will end up with a magnetic field diagram. As we already know, when a current runs through an object, the object generates a magnetic field. The new magnetic field diagram for this electromagnet is slightly different from permanent magnets, but the same principal concepts still apply. The vectors will show how a north pole would react to this magnetic field. We will go over how to figure out the direction of this magnetic field using a right-hand rule during our presentation. Now that you understand the basics of magnetic fields, we will take a look at the electromagnetic train. The train itself is a battery with two magnets that are attached to either end of it. Notice how the magnets are arranged. They are oriented in a way where the same sides face each other. The force of repulsion is definitely present, but their force of attraction on the battery is greater than the repulsion, so they will stay on the battery. These magnets are conductors, and the copper wire is also a conductor, which means that when the train is touching the wire, it essentially creates a circuit. With the current going through the wire becomes an electromagnet with a magnetic field. As the train moves along the track, the circuit will continue moving as the train moves. The magnetic field of the copper coil looks something like this. We have already seen what a magnetic field looks like around a wire with a current running through it, but this magnetic field looks a little different. This is actually due to the shape of the coiled wire, and it results in a magnetic field that looks like the diagram on screen. Take note that on the inside of the coil, the vectors are close together, meaning that the magnetic force within is very strong to the magnetic force on the outside of the coiled wire. This magnetic field interacts with the magnets of the train to propel the train along the track. Essentially, the end of the train is being repelled while the front of the train is being attracted, resulting in the train being propelled forward along the track. We will go over this in more detail during the presentation in class. The train will continue to move until either the battery no longer provides current or a magnet stops touching the track, breaking the circuit.